Section 4.1 is about exponential functions. An exponential function was any function of the form y equals a to the x, where the input was the exponent of the function rather than the base. So one of the things we want to look at is evaluating exponential functions. And it's pretty easy because all you have to do is plug a number in. It's just function notation. And we've done function notation with other functions. So if I give you the function f of x is equal to 3 of the x, and I say find f of 2, you know that all you have to do is plug in 2 for the input, and 3 squared is 9. What if I say find f of negative 2/3? Well, again, all you're going to do is plug in negative 2/3 for the exponent. This is the same as 1 over 3 to the 2/3. And then you had to put that into your calculator to find out what the decimal equivalent is. You don't have to turn it into 1 over 3 to the 2/3. You could just do 3 raised to the negative 2/3. I would put the 2/3 in parentheses, or if you have a calculator that when you do raised to will put the whole thing in parentheses, that's fine. You should get approximately 0.4807. If I say find f of pi, well, as long as you know where the pi key is on your calculator, you should be able to raise 3 raised to the pi. And you should get approximately 31.5442. I'm running out of space. And now about f to the square root, or f of square root of 2. Just put square root of 2 in for the exponent. So 3 raised to the square root of 2. And you should get approximately 4.729. Let's talk about the graphs of exponential functions. I realize you could just shove this into your calculator to see what the graph of an exponential function is going to look like. But let's look at this. Let's look at y equals 2 to the x. You're going to graph it in your calculator, and it's going to look something like this. Except I did that wrong. Let's try that again. It's going to look something more like this. There we go. Sorry. The graph of y equals 2 to the x is going to be this graph that goes up from left to right. It has a horizontal asymptote of y equals 0, or the x-axis. I want you to notice that it passes through 0, 1, and then the graph goes up forever. If you've ever heard the phrase, it grew exponentially, that phrase means it grew fast. The graph of y equals 5 to the x would look very similar, except that it would be more like this. It would grow much faster. And again, it still has a horizontal asymptote of the x-axis, and it passed through 0, 1. And the graph of y equals 10 to the x, if you put that into your calculator, it'll look like this. What I want you to know is the bigger the base, the faster the graph grows. But every single time it passed through 1, 0. I wonder why, or 0, 1, I'm sorry. I wonder why that happened. Well, what is 2 to the 0 power? Anything to the 0 power is 1. So 5 to the 0 power is 1. 10 to the 0 power is 1. All right, let's do this again, except I'm going to change the bases a little bit. This time I'm going to look at y equals 1/2 to the x. The graph of y equals 1/2 to the x is going to look something like this. It still has a horizontal asymptote of the y or the x-axis. It still passes through 0, 1. That's kind of interesting. How about y equals 1/5 to the x? Well, it's going to look something more, oops, that didn't draw very well. It's going to look something more like this. it's going to decrease a lot faster. And y equals 1/10 to the x. Oh, that's going to be very steep to start off, and then it's going to end up like this. And again, all three of them pass through 0, 1, because when you raise all of them to the 0 power, you get 1. So here's a little different definition about what the graph of an exponential function is going to look like, so you at least have a general idea. For an exponential function, y equals a to the x, if a is greater than 1, the graph is going to go up from left to right. And if a is between 0 and 1, the graph of the exponential function is going to go down from left to right. And that'll give you a general idea of what the graphs are going to look like, although I expect you'll probably just put them in your calculator. The other thing that I want to mention is that for both of these graphs, whether they go up or down forever, the domain of all of them is going to be all real numbers, because you can plug every number in the world in for x and you'll always get a number out. However, you don't get every number out. The range, both of these graphs exists above the x-axis. So we're going to say that the range for both of them is y is greater than 0. Not greater than or equal to, because it never actually hits the x-axis, just greater than 0. Another thing that we can do with exponential functions is we can move them around the coordinate plane. We talked about transformations on graphs. So if I start off with the equation y equals 2 to the x, and I ask you, okay, what would y equals 2 to the x plus 3 look like? Well, you should be able to tell me now that that graph is going to move up 3. And if you're unsure if it really does, check it in your calculator. But anytime you add a number to a function, it moves the graph up. And if you subtract a number from a function, it moves the graph down. Well, what is this going to look like if the graph moves left or right? It'll look like this. This would be the exponential function that's been moved to the right 3. If it said x plus 3, then we would have moved to the left 3. Whenever the change is being made to the input, as opposed to the previous problem, where the change was being made to the output. And another thing that we can do is we can reflect the function over the x-axis. Reflect over x-axis. And that always happens when you multiply the original function by -1. The one thing that's really fun about this section is talking about compound interest. I'm a big fan of money problems. I like money. I like to do problems about money. And we actually talked about problems similar to this when we did the mathematics of finance. So we're kind of coming around and talking about it again. The formula for compound interest is a of t equals p times 1 plus r over n to the nt, where a of t represents the amount of money you have after t years. P is called the principal. It's the amount of money you invest in the first place. For example, if Grandma gives you $500 for the holidays, if you go put that in an account, that would be the principal. T, little t, is the number of years that you're going to leave the money there. R represents the interest rate per year. And N represents the number of times the interest is compounded in a year. There are several different ways we can compound interest, and I want to talk about those. They are annually. That means you compound the interest one time per year. Semi-annually. That would be twice a year. Quarterly. That's how most banks give you interest if you have a savings account. They compound your interest 4 times a year. Monthly would be 12 times a year. Weekly would be 52 times a year. Daily would be 365 days a year. We're not going to worry about leap years. Hourly. What would hourly be? Well, if there are 365 days in a year and every day has 24 hours, hourly would be 8,760 times per year. Let's talk about how to do a compound interest problem. A sum of $1,000 is invested at an interest rate of 12% per year. Find the amounts in the account after 3 years if interest is compounded annually, semi-annually, quarterly, monthly, and daily. All right, so let's start with the first one, which is annually. The amount of money in the account after 3 years is going to equal the principal. You invest 1,000. 1 plus the interest rate is 12%. Now remember, when you're dealing with percents, you got to turn it into a decimal. So 0.12 divided by, annually means we compound once per year, raised to the NT. 1 times 3 is 3. And then all you have to do is plug that into your calculator. And you're going to find out that you'll have $1,404, 1,404, that's right, and 93 cents. Remember, this is a money problem, so we always round to the hundredths place. All right, how about if we're going to do this semi-annually? Well, semi-annually, the principal's still 1,000 plus. The interest rate's still 12%, but this time we're going to divide by 2. And we're going to raise that to the 2 times 3, which is 6. You plug it in your calculator and you find out you have $1,418.52. Now let's do quarterly. Quarterly is 4 times a year. So 1,000 times 1 plus 0.12 divided by 4 raised to the 4 times 3, which is 12. Remember, we're raising it to the n times t, the number of compoundings times the time. I plug that in my calculator and find out I will have $1,425.76. Now let's do this monthly. 1,000 times 1 plus 0.12 divided by 12 raised to the 12 times 3, which is 36. And I'm going to find out that's $1,430.77. Now let's do this daily, which is 365 times a year. So 1,000 times 1 plus 0.12 divided by 365 raised to the 365 times 3, which is 1095. And I'm going to have in my account $1,433.24. Now what I want you to notice is that the more times I compound a year, I make more money. But it's not a huge amount of money, is it? It's kind of interesting. The last thing that I want to talk about is something called calculating the annual percentage yield. The annual percentage yield is something called the simple interest. There, that looks better. Simple interest that one would yield, or I'm sorry, I should say it's a simple interest rate that yields the same amount at the end of 1 year. That means instead of compounding daily, if we were only compounding 1 time per year annually, what would that interest rate be? It's not going to be 6%. So this is what we're going to do. We're going to start with our formula. the amount of money we're going to have after a certain amount of time is equal to the principal, which I don't know what that is, but that's okay. 1 plus the interest rate, 6% is 0.06, divided by 365, because we're compounding daily, raised to the 365 times 1, because we want to only do this for 1 year. Now, what I'm going to do is I am going to evaluate this part in my calculator real fast. 1 plus 0.06 over 365 raised to the 365 is approximately 1.06183. Now, I'm going to go to this. The formula for simple interest is A equals P 1 plus R. Well, if I want to find the simple interest that yields the same amount after 1 year, I'm going to take this and set it equal to this. So 1 plus the rate must be 1.06183. You subtract 1 and you get 0.06183. Well, that's the interest rate. Let's make that a decimal again. To make it a decimal again, you multiply it by 1,000, and we find out that the interest rate is 6.183%. So if I wanted to find the interest after 1 year, the interest rate would be 6.183%. I would have the same amount of money that I would get if the interest were 6% on the nose and I compounded daily.